Okay everyone, so this is going to be a GCSE Combined Science Trilogy higher tier past paper walkthrough for Chemistry Paper 2. And this was the paper that was sat in June 22. So I'm going to go through it and model it how I would have done it. And the link to the past paper and the mark scheme is in the description. So a student investigated the colours in brown ink using chromatography. Figure 1 shows the apparatus used. Give 2 errors made by the student. Describe the problem each error would cause. Now, when you did chromatography as your required practical, hopefully your teacher would have identified 2 common errors that people often do. Look at the labels that they've given you. You've got a start line drawn in ink. Hopefully remember, it should be drawn in pencil. And then your solvent, you can see the water or whatever solvent they've used is much higher than the actual ink itself. That should be much lower. So what you need to then do is explain what issues these errors are then going to cause. So if I say error number 1, start line drawn in ink, and error number 2, you should say the solvent is too high / above the ink dots. So you identified your errors, but then you need to say why they are going to affect the result. So if your start line is drawn with ink, well, it's going to contaminate or affect your different dots of ink. So the problem is it will also mix or dissolve in the solvent. And obviously you want it just to say where it is as your start line. Problem number 2, if your solvent is too high, what could effectively happen is the colours will wash off or dissolve in the solvent. They would all stay in the water and not move up the paper. Okay, it's always, in pretty much every past paper question, if it talks about errors, odds are it is those 2. A different student set up the apparatus correctly. Figure 2 shows the results. You've got figure 2 there. Give 2 conclusions the student can make from figure 2 about the 4 colours in the brown ink. So you've got brown ink dots there. What conclusions can you make about it? Well, remember, if the dots are the same level, odds are it's the same substance. So I could say brown ink contains red, yellow and blue ink. Okay, it does not, or it doesn't have one substance it contains that doesn't match with anything, and it does not have any green. So I could say there's no green colour in the ink, and I could also say that there is an unknown substance. Okay, in the ink. Okay, so that's 3 conclusions there. You only needed 2 of them. Question 1.3. Why was the green colour still on the start line at the end of the experiment? The experiment was left for too long, the green colour was insoluble in the solvent, the green spot contained too many colours, or the green spot was too small. Well, hopefully you remember that inks go up the paper based on their solubility or their attraction to the mobile phase. Substances that are insoluble do not move. So it should just be, because it was on the start line, okay, hasn't moved, so therefore it's insoluble. The same reason why your pencil line is insoluble and doesn't move. A student calculated the RF value of a colour to be 0.24. The colour moved 1.8 centimetres from the start line. Calculate the distance the solvent moved. Okay, so you've been given the RF value, which is 0.24, and you've been told the colour moved, distance moved by the colour was 1.8 centimetres. You want to calculate the distance moved by the solvent. So what you'd then have to do is rearrange the equation. So distance moved by the solvent would be your RF value, 1.8 centimetres over 0.24. Put that into your calculator, gives you a distance of 7.5 centimetres. Okay, and that would be your 3 marks there. And that's the end of question 1. Question number 2 then. Water that is safe to drink is called potable water. Compare how easily potable water can be obtained from wastewater and groundwater. Wastewater is your sewage, fresh water is groundwater. Okay, so I should immediately be thinking wastewater, well, that is much, much harder to get potable drinking water from. Ground fresh water, that's easier. Okay, so 1 mark just for identifying that. So I would say wastewater is much harder to obtain potable water from. Fresh water is easier. So now we need to explain why. Okay, I would say wastewater treatment contains many more steps, is longer, and requires more energy. Okay, whereas fresh water has fewer steps and is quicker. So you've got some quick comparisons down there, which hopefully should be pretty obvious. However, we then need to explain why. So this is when going into and you need to demonstrate your knowledge of these different processes. So I would say fresh water is filtered to remove solid objects. And is then sterilised using UV, chlorine or ozone. It is then potable. So it's a really short process. Wastewater requires screening to remove those large objects. It is then put into a sediment tank. Okay, so you know it's put into a sediment tank where it separates into sludge and effluent for hours. Okay, so that's what takes a long time. It's got to separate out into the heavier, denser and less dense parts. Once it's separated, the sludge and the effluent are then treated differently. The sludge and effluent then need to be treated. Sludge is anaerobically digested. You've got to remember which way round it goes. So sludge is anaerobically digested and forms fertiliser and biogas. Okay, as it's digested, effluent is aerobically digested. Okay, and as it's been aerobically digested, that then can be released back into the environment, which can then be released as fresh water but it still needs to be treated to get it back into potable water, but still needs processing as fresh water in the process up here to make it potable. So obviously it's much longer. Now you don't need as much as that to get 6 marks. You could have missed some things off, but that's just demonstrating a clear understanding of how we treat wastewater and fresh water. A scientist produced potable water from 150 centimetre cubed of salty water. Which process can be used to produce potable water from salty water? Well, the first one that jumps out at me is distillation. Okay, but look at the other ones. Electrolysis wouldn't just leave us with potable water. Filtration wouldn't, because the salt would just pass straight through it. Sterilisation isn't an actual scientific process, or you wouldn't leave us with potable water. That's to get rid of bacteria, etc. So it must be the first one, which is distillation. Salty water contained sodium chloride. The student collected 2.4 grams of sodium chloride from 150 centimetre cubed of salty water. Calculate the concentration of sodium chloride in grams per decimetre cubed. So this is going back to the equation that we actually need from came up in chemistry paper 1. Concentration is mass over volume. Okay, and we want it in grams per decimetre cubed. So therefore my units must be grams and my volume must be decimetre cubed. So I can see my grams are fine, 2.40 grams, divided by my volume, but my volume is in centimetre cubed. Decimetre. I should remember there's 1,000 centimetre cubed in a decimetre cubed, so I would divide it by 1,000 to put it into decimetre cubed. So it should be 0.15 decimetre cubed. If I do that sum, that gives me an answer of 16 grams per decimetre cubed. And that is the answer. That's the end of question 2. Question number 3 then. This question is about the reaction between sodium thiosulfate solution and hydrochloric acid. The equation is given below. The mass at the end, or the mass of the conical flask and the contents was greater at the start of the reaction than at the end. Explain why. So I've been told the mass at the beginning was more, the mass at the end was lower. Why might this be? And they've given me the equation, so I look carefully at it. I've got 2 solutions, and then I can see I've got a solution here, a liquid, a gas and a solid. Which of these might have caused my products to then decrease in mass? Well, it's my gas. So therefore, 1 mark would be sulfur dioxide is produced. Okay, which is a gas. The gas then escapes from the container or flask, or conical flask. Okay, so 1 mark for recognising that the gas that you make, anytime a gas is made, your mass will go down, and that's because it's escaping, it's going into the surroundings, the atmosphere, and therefore it's not being measured anymore. A teacher demonstrated the reaction between sodium thiosulfate and hydrochloric acid. Figure 3 shows the experiment, and the experiment was done in a fume cupboard. Okay, so hopefully you remember this required practical of the disappearing cross, and this is the method the student used. You pour 50 centimetre cubed of a thiosulfate solution into a conical flask. You put the conical flask on a black cross. You pour 10 centimetre cubed of hydrochloric acid into a beaker, and then you start a timer. You stop the timer when the cross can no longer be seen. You repeat the experiment at different temperatures. Okay, so what type of variable is the time in this reaction? Independent, dependent or control? Independence what you change, dependence what you measure, controls are what you keep the same. So you're changing the temperature. What are we then measuring? Okay, well, we're actually measuring then, I'm using a timer, I'm measuring the time when the cross can no longer be seen. So my time here is my dependent variable, is what I'm measuring. I should then keep other things like the concentration of the solutions, the amounts of the solutions, those would be my control variables. Question 3.3, table 1 shows the results, and it gives you a graph, table, and you've got to complete the graph. Plot the data from table 1 on figure 4 and draw a line of best fit. They've given you scales, which is nice. There's 3 marks on a higher tier paper, so the plotting is what they're actually assessing, and you can see here relatively different numbers or challenging numbers, so you've got to make sure it's as accurate as you can. So I'd go 19 degrees Celsius to 82. Take it one at a time and then mark it off. So I'm going 19, which would be here, up to 82 and reading my scale here. So each little square, gap of 10, 5 squares. So each little square is worth 2. So I'd just be 1 square up. And you've got to be within half a square of that point. Okay, in order to get all 3 marks, or well, 2 marks of the plotting, you've got to be really accurate, and you've both got to be all correct. So 19 was 82, 32 was 48, so I go to 32, and then 40, one below 50, tick that off. 45 was 43, so they go bang in the middle, and then it's 43, so 42, 43. Okay, then I've got 52, which is 15, so 52, which is bang in the middle, 15. Okay, and then 63, which is 7, 63, so 62, 63, which was just below, so 2, 4, 6, 7, and then 73, which is 3, so 73, which would then be 3, so just above 2, which is there. Okay, so then you can see here, you've got to then draw a line of best fit. So I've plotted my data on, but obviously higher tier paper, you plotted on your points, which is fine, but we need to draw a line of best fit. For this graph here, you've got a weird result that's kind of making it not look right. That would just be your anomaly. You don't include your anomaly in your line of best fit. Turn your page to make it easier, and I would draw a smooth line of best fit going for as many of the points as possible. Okay, if you had tried to include and change your line of best fit going like that, you would have lost that line of best fit mark. Okay, so that is the graph question. A student investigated the effect of the concentration of thiosulfate on the time taken for the reaction at room temperature. Figure 5 shows the results of a tangent drawn at 0.4 mole per decimetre cubed. Calculate the gradient or the slope of the tangent at 0.4. And they've given you the tangent has been pre-drawn for you. Okay, so what you then need to do, what I would be doing, if they've given you a tangent, I would then connect my tangent and make it into a triangle. Now you can do it, you don't have to do it the full width. In fact, I think I might make it easier on myself, and I'm not going to actually do it to the full point. I'm just going to do it to that point here. Okay, now it doesn't matter which points you use to make your triangle on your tangent, because it will be the gradient. If you've pulled off the right points from your graph, it should be the same number. So what you would then do is to find the gradient of the curve of the tangent is your change in your y value divided by the change in your x value. So I can see on my y value, obviously you guys would be using a ruler, making sure it's as accurate as possible. My one goes a bit wonky on the iPad. But my change in my x value, I've gone from 7 all the way up to 12, 14, 15. So my change in my y value is 8. My change in my x value, I've gone from 0.1 up to 0.52. Okay, oh no, 0.54. Okay, on this point here. So my gap here is gone up by 8. My gap on my x-axis has gone up by 0.54, because it started at 0.1. It would have gone up by 0.44. Okay, so you get 1 mark. It doesn't actually matter what numbers you choose to pick off. You get 1 mark if you've chosen your y value correctly. You get 1 mark for your x-axis. Okay, you can then divide it, and then if I did 0.8 over 0.44, do that on my calculator, 8 divided by 0.44, that gives me a gradient of 18.18 recurring on my calculator. I'll just leave it as 18.18. And then you need to give the answer. So I give my gradient as 18.18. Okay, so question 3.5 then. The student determined the rate of the reaction at regular time intervals during the experiment. Explain why the rate decreased during the reaction. You should give your answer in terms of particles. So hopefully what you should remember in a chemical reaction is that the rate always starts off fast, and then it will level off, slow down, and then plateau, and then finish. We've got to explain why in terms of particles. So why is our rate decreasing as time goes on? Well, what's happening is the thiosulfate particles are being used up. The acid particles are also being used up, but it's the thiosulfate that makes the sulfur. So the thiosulfate particles are being used up per, and this is the key phrase, per unit volume. Okay, so it's basically saying in each solution, per unit volume, the amount of thiosulfate particles are being used up. So therefore, so this is linking it back to collision theory. Remember, in order for a reaction, particles need to be able to collide. So therefore, the chances of collisions, or successful collisions, decreases. And that would be your second mark. 1 mark for recognising thiosulfates being used up, 1 mark for recognising that will lead to a decrease in collisions and therefore a decrease in your rate. Okay, question number 4 then. This question is about hydrocarbons and the uses of hydrocarbons. Figure 6 shows a model of an alkane. What is the name of the alkane in figure 6? Remember, there's only 4 alkanes that you have to remember. It's when we've got 1 carbon, 2 carbons, 3 carbons and 4 carbons, and it goes meth, eth, prop. So the one with 4 carbons is butane. Okay, so methane has 1 carbon, ethane 2 carbons, propane 3 carbons. Butane, because it has 4 carbons in the middle, would be butane. What actually is a hydrocarbon? Well, I would say it's a molecule or a compound that only contains, and the key thing is only containing, hydrogen and carbon. Large hydrocarbon molecules are cracked. Question 4.3. When C11H24 is cracked, 3 products are formed. Complete the equation. So this is just a little bit of a puzzle question, because you've got C11H24, which is your reactant, and we know that it's going to be broken down into our products. So the key thing is we've just got to have the same number of atoms on our left-hand side as our right-hand side. So you've been given a 2 here, so you know you're going to have to double something or whatever you put in there. And you've got to then just make sure the atoms then balance. So there are various ways of doing this. So what I might then do is that you know that you've got an alkene here. Now when you crack something, you make an alkane. and an alkene. Okay, now the smallest alkane that we can make is C2H6. So that gives us in total 4 carbons that we've got here, and 2 lots of H6 gives me 12 hydrogens. I've got 5 carbons from over here and then 10 hydrogens. So in total, I've used 9 carbons across both of these molecules and 22 hydrogens. So therefore, I just need to then see what I've got left. Well, going back to over here, I've got missing 2 carbons because I started with 11. So my next product must be C2. And then I'm missing also 2 hydrogens here. Okay, I've got 22, but I started with 24, so it must be C2H2. So there are different ways of doing it, but that's what I would have gone with, and that would get you the marks. Question 4.4 then. Explain why one of the products of cracking is in high demand. So this is just knowing why do we do cracking. Well, the whole reason we do cracking is to make short-chained alkanes. And why are they useful? Because they make very, very good fuels. So I would say C2H6 is useful as a fuel because it is more flammable. Question 4.5. Window frames can be manufactured from wood or plastic. Table 2 shows data from a life cycle assessment for a wooden window frame and a plastic window frame. Both window frames are the same size. So you've got information about wood and plastic. You've then got loads of different information here, like sources of hydrocarbons used in the production in kilograms, the greenhouse gases released, the oxides of nitrogen and sulfur dioxide, waste materials, energy consumption in production, and the lifetime cost. We've given you loads of information, and the question is, evaluate the sustainability of wood and plastic frames. You should include environmental and economic factors. So obviously environment and economic to do with money and cost. Okay, so in this life cycle assessment, they've given you loads of information, and we just need to make sure that we're relating and using some of the key points they've given us in the table. So everyone can get a couple of marks on this question just by referencing what they've given you and explaining what it shows, but then also linking in some of your own knowledge will help you get to those top grades. So first of all then, if I'm comparing wood and plastic, I would then be thinking about, first of all, where do they come from? So first part of the life cycle assessment is raw materials. Wood obviously comes from trees, plastic is oil. So first marks that I could say is wood comes from trees and trees are renewable. Okay, whereas plastic comes from oil, which is not renewable. Those are the key things that you could start off by saying. So that's an immediate advantage for wood, not at a disadvantage for plastic. Okay, the sources of hydrocarbons that are used for production, you can see that plastic uses a lot more hydrocarbons. So that would be a negative. Wood uses much fewer. So another point I could say is that plastic produces or uses a higher amount of hydrocarbons, and then thinking about what do I know about hydrocarbons? Well, they're generally bad for the environment, but I link that onto my next part. Greenhouse gases released during the production, use and disposal in the equivalent of CO2. Well, you can see again plastic is releasing more CO2, whereas wood is producing less. Now, you could link in a bit of your own knowledge here. All this CO2 we're releasing, what is that contributing to? Climate change or global warming. Okay, so plastic window frames are having a bigger effect on the environment than wood. Oxides of nitrogen and sulfur dioxide produced in arbitrary units. You can see again, plastic are producing more, okay, than wood window frames. So that's an advantage for wood. Now, oxides of nitrogen and sulfur dioxide. These are two of the pollutants you need to know about. Oxides of nitrogen cause respiratory problems. Sulfur dioxide causes acid rain. So I could be making the point that plastic window frames causes more acid rain and more respiratory problems than the manufacture of wood window frames. The waste materials that are produced, again, plastic produces a lot more, wood a lot less. What is the disadvantage of loads of waste materials is that solid waste goes to landfill. So plastic is producing a lot of waste that would then go to landfills that are then being used up and space is diminishing. The total energy consumption of making them, again, worse for plastic, better for wood. So you've got a whole list of disadvantages for plastic window frames and a whole list of advantages, but the final one, in terms of the cost, wood window frames, specifically down to their maintenance, compared to plastic window frames, wood window frames are more expensive, so that is your negative, but plastic are cheaper. So when you do your answer, using the points that I've just said, you'd be saying all the negative things of environmental factors for plastic, but the big economic one advantage is, that is for plastic. So you're effectively putting all this information here into short bullet point sentences, comparing them. Remember, a great comparison word, whereas, and that would give you, from what I've just said, 6 marks in that answer. Okay, question number 5 then. This question is about the Earth's atmosphere and the Earth's resources. After the formation of the Earth's early atmosphere, the amounts of nitrogen and oxygen in the atmosphere have changed. Explain the main changes in the amounts of nitrogen and oxygen in the Earth's atmosphere. Well, hopefully we know that the Earth's atmosphere is about 79% nitrogen now and about 21% oxygen. So both have increased, but it's saying, so you can say starting off, nitrogen has increased and oxygen has increased, but we've got to say why. Nitrogen has increased because of 2 reasons. First of all, it was given off by the volcanoes in the Earth's early atmosphere, okay, and also it was produced by denitrifying bacteria, okay, by bacteria in the soil, and gradually, because nitrogen is a really unreactive gas, it's built up in the atmosphere over billions of years or millions of years. Oxygen has increased. Why has the oxygen increased? Well, it's because of the evolution of plants, okay, so it's all down to photosynthesis, increasing the amount of oxygen in the atmosphere. Question 5.2, describe how coal was formed from the carbon dioxide present in the Earth's early atmosphere. 4 marks. Okay, now the key fact you have to know here is that coal comes from the remains of dead plants. So whilst oil comes from the remains of dead plankton and dead sea creatures, okay, from millions of years ago, coal comes from the remains of dead plants. Okay, so how is it linking to carbon dioxide present from the Earth's early atmosphere? Well, I would say carbon dioxide was absorbed by photosynthesis in plants and trees. Okay, so it was converted into the glucose in the plants and trees. What then happened to turn it into coal? The plants and trees died, and over millions of years, were converted into coal. So it's basically just showing the carbon dioxide, yes, absorbed by the plants then died and then turned into coal when they were buried, and then the pressure coming from the sediment above and the heat from the Earth's core. Okay, but this question is specifically asking how over time did it change, so you don't need to go into the pressure and heat. The combustion of 1 kilogram of coal produces more carbon dioxide than 1 kilogram of natural gas. Suggest why. So, why is basically coal producing more CO2 than natural gas? Well, it probably just has higher amounts of carbon. Okay, because if you have more carbon, you have more carbon dioxide. Coal has a higher percentage of carbon than natural gas. Metals are extracted from metal ores found in the earth. Describe how bioleaching, that's your keyword, is used to extract copper from low-grade ores. So you should remember bioleaching is one of your sustainable ways of getting metals from the earth when they're using low-grade ores. So we don't use the traditional blast furnace, we use bioleaching or phytomining. And you basically got to explain what bioleaching is. So you could break it down. What's the key thing about bioleaching? What does it use? Bioleaching uses bacteria, 1 mark for saying that, which breaks down solutions of copper called leachates. Okay, a leachate is just a solution of copper. Okay, and then the bacteria break it down, and then the leachate can then be electrolysized or displaced to give us the copper. Okay, so 1 mark for identifying its bacteria. Okay, the bacteria is then added with the ore and makes leachates, and the leachates can then be used to displace the copper. We then got a calculation here. Phytomining uses plants to extract nickel from low-grade ores. Plants contain 0.792% nickel by mass. Plants are burned to produce the ash. The ash from these plants contains 4.8% nickel by mass. Calculate the mass of ash produced from burning 1,000 kilograms of plants. Give your answer in grams in standard form. So calculation 1, if we break down what we've got, we know we're using 1,000 kilograms of plants. And first of all, we know that plants contain 0.792% nickel by mass. So what we can first of all do is work out how much nickel we're effectively making from that from this. Okay, so if I've got 1,000 kilograms of plants and I want 0.792%, okay, divide it by 100, divide it by 100 times by 0.792 gives me 7.92 kilograms. So within my plants, there are 7.92 kilograms of nickel. That is my first thing that I can do. But I want to calculate the mass of ash containing 1,000 kilograms from 1,000 kilograms of plant. And I'm then told that ash from these plants contain 4.8% nickel. So the ash only has 4.8% of the nickel in it that I've just calculated here. So I can do 7.92 over my 4.8% off the percentage of nickel. Okay, then times it by 100% because I don't want 4.8%, I want 100%. So that would then give me 165, but this is in kilograms, so 165,000 grams. Okay, now last thing is ask for it in standard form, so it would be 1.65 times 10 to the power of 5. So 1 mark for getting to 7.92, 1 mark for realising that you can divide it, okay, 1 mark for getting to 165,000, 1 mark for putting it into standard form. And that's the end of question 5. Okay, question 6 then. This question is about catalysts and equilibrium. Which type of substance is a catalyst in biological systems? So, when have you learnt about a catalyst in biology? Well, algae is a plant, so that's not it, or water plant. Alkenes are chemical. Formulations are just mixtures. Enzyme should be the word that you would have heard in biology, which is a catalyst. So explain how a catalyst increases the rate of a reaction. So you know catalysts increase the rate, but how do they do it? Well, there are 2 phrases you always have to use when you describe a catalyst. Is that catalysts, first of all, provide an alternative reaction pathway. Okay, so instead of just going from A to B, that might need a certain amount of energy. It could go A, C to B, which would then need less energy. And that is our second part, which has a lower, and you have to say exactly, activate a lower activation energy. Okay, so instead of just going A to B, that might need 10 joules of energy. You might go from AC to B, that might only need 4 joules of energy. So therefore the alternative or reaction pathway needs less energy, and therefore the particles are more likely to have enough energy to then do those collisions, successful collisions, and therefore the rate increases. The reversible reaction for the production of ammonia is given below. What can scientists predict using Le Chatelier's principle? Well, it's all about the equilibrium, or the position of the equilibrium. We can predict, is the forward or the reverse reaction going to increase and be at a faster rate? And that is saying the position of the equilibrium. So we can show the effect of changes on the equilibrium of reversible reactions. Describe how a reversible reaction is able to reach equilibrium. So imagine you've got these chemicals in a container. How are they going to reach equilibrium? Or what does it mean when they've reached equilibrium? Well, equilibrium is reached when the forward reaction is the same rate, key word here, rate, as the reverse reaction. And this happens in a closed system. So remember, a closed system is one that is totally isolated, no energy or particles can be added or removed from it. So equilibrium has to be in a closed system, and that gets you the second mark. Explain the effect of increasing the pressure on the yield of ammonia. So remember, using Le Chatelier's principle, if I increase something, so I'm coming along here, I'm increasing the pressure, so the system will try and decrease the pressure. So I always think about these questions in terms of, right, what am I doing? What would the system then do, which is the opposite? Is that going to favour the forward or reverse reaction? And therefore, what is that going to do to the amount of product or the yield of what I'm doing? So 4 steps. So in this situation, in terms of pressure, remember it's all about reactants and products. When I'm talking about pressure, I'm looking at the amount of moles. There's no number, it's a 1. So I've got 4 moles on my left-hand side, but 2 moles on my right-hand side. If I come along and I increase my pressure, what I am then going to do, or what the system is going to try and do, is decrease the pressure. So if I increase the pressure, the system will decrease the pressure. To decrease the pressure, it will shift more of the gases to where there's less molecules, so it will increase the forward reaction. Okay, so it will favour a forward reaction, and that would make more ammonia. Okay, so what I would then say is, explain the effect of increasing the pressure on the yield of ammonia. Increasing pressure increases the yield of ammonia as the forward reaction increases as more particles, as more moles are on the left-hand side compared to the right. Okay, so I'm saying the yield will increase because the forward reaction is going to increase because we're going from the 4 to 2. Okay, so the forward reaction would increase. The reaction to produce ammonia is exothermic. Explain the effect of increasing the temperature on the yield of ammonia. Okay, so if I go back to my equation, you've been told this time the forward reaction is exothermic. Okay, remember exothermic releases heat, so therefore the reverse reaction must be endothermic. If I am coming along and I'm going to increase the temperature, the system will try and decrease the temperature. Which one would that favour, the exo or the endo? Well, endothermic, so it will favour the reverse reaction because that would bring down the temperature. Favours the reverse. So the reverse reaction would be happening faster. So what's that going to do to my ammonia, which would decrease my yield? Okay, so going back to the question, increasing temperature would decrease the yield as the equilibrium of the system favours the reverse endothermic reaction. Okay, so therefore, that actually is the end of the questions. Okay, and just 2 marks on Le Chatelier's principle at the end. This is the higher tier topic in this unit, so yeah, it's normally at the end of the paper. But that is the end of this chemistry paper then. Hope it was useful. And yeah, remember the link to the mark scheme and the question paper are in the description. Thank you very much.